All right, so this is 2.2.3. Energy levels and photon emission. So last time I introduced the concept of having different energy levels, and we talked about how electrons might not necessarily gain enough energy to escape its material or escape its atom. So today we're going to look at what happens if the electron gains some energy, but it doesn't gain enough energy to be liberated. So the electrons can do different things. So what happens if the electron is not liberated? So the energy wells have discrete levels. So at the very bottom is what we call the ground state. This is where electrons normally would rest in their energy levels. If they gain some energy by absorbing a photon, or if they were to absorb some kinetic energy from a nearby passing free electron, these electrons can now become excited. When they're excited, they jump to a higher energy level. But the energy has to be exact. It can't sit halfway between two energy levels. It can either be at one energy level or it can be at the next. So it has to have enough energy to get there. So we'll call this down here the ground state. This here is called the first excited state. This will be the second. This will be the third. And up here will be liberated. So these energy levels are usually given in terms of volts. So in this example, on the ground state, we're going to have minus 13.6 volts. Just fix that, 13.6 volts. The first excited state in this example is minus 10.2 volts. The second excited state, minus 3.2 volts. And these levels will be different depending on what material we have. So these will be given to you. You don't need to memorize what the different energy levels are for different materials. But there are some rules that we need to follow when we're talking about quantum. And really it's what the word quanta means anyway. Quanta comes from the word quantities. There are quanta of energy. So it's discrete rather than continuous. Yes? Yeah, so the energy of the electron at minus 13.6 volts will be minus 13.6 volts times by the charge of the electron. In other words, minus 13.6 electron volts. No, so that's the energy that's binding it. To go up to the first excited state, it has to have the difference between those two energy levels. Yeah? That's also why it's negative, because for the electron to fall into the well, the electron doesn't need to do work. Work is done on it. So the electron doesn't need to spend any energy to get into the well. The well will drag the electron in anyway. Hence why the numbers are negative. Yeah? Otherwise, if it was positive, that means that the electron has to do work to get into the well. But the electron doesn't need to do any work. Right, we'll look at the quantum rules next. So for an electron to reach the excited state, it has to have exactly the right amount of energy because they're discrete levels. As I mentioned earlier, it can't sit halfway between two different energy levels. And this energy can be gained in two ways, either by an incident photon on that electron. So the electron will absorb that photon and will gain energy in order to get to an excited state. Or it can take this energy from a passing free electron. So when we talked about the cathode tubes last time, we talked about the mercury vapor absorbing the energy from nearby free electrons, which is from the current, right? As that current is flowing, those electrons are moving. If they're moving, they've got kinetic energy. The electrons bound in the mercury vapor then gain some of that kinetic energy from those electrons. They then excite, de-excite, and emit ultraviolet radiation, or ultraviolet photons, I should say. So this energy can come from A, an incident photon, or B, by taking some energy from a passing free electron. They interact with each other. Electromagnetic interaction. Virtual photon. So it will only take what it needs as well. It won't take everything. It would what? Yeah, so there will be a change in the momentum of the passing electron. It could change direction. It could slow down. It won't speed up because it will lose some energy. But it could carry on in the same direction and slow down. It could change directions as well. Depends on how the interaction happens. But that's a lot more complex. You won't need to know about that. You just need to know that some of its energy can be taken. So electrons that become excited, they jump up to a higher energy level. Once they reach that excited state, they realize that there's nothing actually going on there. So they get a bit bored and they jump back down. And when they jump back down, they have to release the energy that they had originally. So they release that energy as a photon. And this is what happens again in the mercury gas. The electrons excite, but they can't stay excited forever. So they de-excite, and that de-excitation emits a photon. And that energy of that photon corresponds to the difference between the two energy levels that the electron jumped by. So if we go back up again, you'll see how I labeled it as a first excited state, second and third, and so on. It could have multiple states. Some materials will have less states than others. But if we excite from the ground state all the way up to the third, for example, we can jump back down in different ways. So sometimes an electron might decide it's going to go in steps. So it goes third, second, first, ground. And each time it jumps one step, it releases some energy. And the energy corresponds to the difference between the two energy levels. Sometimes the electron might say, right, I'm going to go from the third straight to ground. And so in that instance, the energy it releases corresponds to the difference between the third and the ground state. So you look at the difference between those two energy levels, and that's what gives you the energy of the photon. And that's also why you get different colors. So some jumps might release red light. Those will be smaller energies. Larger energies might give you green light. Even larger energies might give you blue light. Very large energies will give you ultraviolet. Yeah?
So can you control whether the electron does a massive jump or steps?
No. Depends on the material. That's why we use mercury vapor, but then because we know mercury likes to give us UV, we then have to coat it, the cathode tube, we have to coat it with phosphorus or phosphor coating.
So the behavior in which it takes to get from ground state depending on the
Yeah.
material.
Right, last bit we'll add on. An excited electron will jump back to the ground state and emit a photon with energy corresponding to the potential difference. And this is called de-excitation. Now you can look at what frequencies a photon a material emits, and you can plot that on something called an emission spectra. You might have seen that before at GCSE, for example, in space topic, where you look at the emission spectra of different stars. And then by looking at the emission spectra, you know what the stars are made of, because different materials emit different frequencies because of their different energy levels. And they might also emit different combinations of frequencies. At the same time, materials also absorb different spectra. So you can also look at an an absorption spectra as well to see what they're made of. Anyway, we start a new page. And I'm going to sketch some energy levels. Notice how the first few are close to each other. The one at the bottom has a bigger gap between itself. So the change from there to there is what gives us the change in energy. That energy is going to give us the photon energy. But depending on how the jumps occur, we get different kinds of photons. So, yes?
The first and second meant to be closer than the second and third one.
Yeah, so these two are almost the same, and then just the bottom one draw it a lot more different. So if we had this situation where we went from up there all the way down, that's quite a big energy difference. So a very, very large difference in energy will give us a violet photon. But what else could happen is we could have an energy jump that goes from there to there, and then from there to there. So if we went from there to there, that's not a very big energy difference. It's quite a small energy. So that could correspond to, for example, a red photon. And for the second jump, that's a bigger energy difference, but it's not as big as the first one. So that could, for example, correspond to a green photon. Now, if you think about it, if this is occurring constantly with lots and lots of different electrons, some of them are emitting violet or blue, some of them are emitting green, some of them are emitting red, depending on these different jumps, then overall you end up having white light, which is a mixture of all these different colors. So that's how the phosphor coating on a cathode tube works. And the colors tell you what material it's made of. I'll put here the frequencies. So what we do is we go back to the energy of a photon, which is equal to hf, and we equate that to the change in energy from one of those jumps. So hf equals to delta E, and delta E just means one of the E's minus the other one. So we could also write that as hf equals to, it depends how we label this. If we label the first one as E1 and the second one as E2, then we'll do E1 minus E2. Put a box around that. Define bigger.
The value greater.
Define greater.
With a high number.
Define higher number. All right, so it depends what we're talking about. Are we talking about the magnitude of the number?
Yeah.
If we're talking about the magnitude of the number, then no, because the ground state obviously has a higher magnitude. But we'll take E1, for example, as being a higher excited state. So for example, if we did before, we had first excited state was 10.2, minus 10.2, and the ground state was minus 13.6, yeah? So if you want to find a difference, you'll do 10.2 minus 10.2 and find the difference between that and minus 13.6. So if you do minus 10.2 minus 13.6, because difference, you have to minus it, minus minus becomes a plus. So you've got minus 10.2 plus 13.6. That gives you an energy that's given to the photon of 3.4. And that's in volts. So then you have to change that to an energy. So to change to an energy, it's electron volts, yeah, EV. And if you change that to joules, you'll basically do 3.4 times 1.6 times 10 to the minus 19. That'll turn it into joules. Then you can plug it into there and work out the frequency. We're going to do an example now anyway, so it'll make sense. All right, let's do an example. So first I'm going to draw some levels, energy levels. So that one should be close, this one should be further, and this one should be much further. Actually, no, it shouldn't. It should be closer. So here we've got 0 volts. Then we've got minus 3.2 volts. Then we've got minus 10.2 volts. And at the bottom, minus 13.6 volts. So for part A, we want to calculate the energy and frequency of an emitted photon when an electron makes a transition from the second excited state to the ground state. So when an electron makes a transition from second excited state to ground state, calculate I, the energy of photon, and I, the frequency of the photon. Then for part B, we say what frequency photon would make an electron jump to the first excited state and then part C, which is connected to part B, what wavelength okay, it's glitched out. What wavelength is this? And you can pause the video here to have a go at the questions, and then unpause the video when you want to go through the answers. All right, so to do the first bit, when an electron makes a transition from the second excited state to the ground state, calculate the energy of the photon. So the energy of the photon, first let's label these up. That's the second, that's the first, and that's the ground. So the energy of the photon is going to be determined by this jump here, delta E. So AI, so delta E is equal to E1 minus E2, which is equal to minus 3.2 minus 13.6. So that delta E is equal to, what is that? 10.4? 10.4 electron volts. Now, if we want to, and we should want to, we want to turn this into energy in joules. So to work out the energy in joules, we'll do 10.4 times by 1.6 times 10 to the minus 19 joules. What does that equal to? Someone types it into a calculator. What does that equal to? 1.66 times 10 to the minus 18 joules. Because volts is not energy. Volts is not a unit of energy. Okay, because that just tells you about the potential of that well. But the potential of that well is not an energy, because it depends on what's in that well. Right? It's the same as if we're on the earth, your height above the surface of the earth corresponds to different potentials, but that doesn't mean that's how much energy you got, because the energy that an object will have also depends on the mass of the object. So, in other words, think of that as the earth. If it were the earth and I had a pencil and I had a bowling ball at the same excited state, do they have the same energy? No, they don't. They might be at the same height, but one has more charge than the other. In the case of gravity, the charge is mass. So it depends on how much charge the thing has, and the charge comes from the electron. So that's why we do EV, the electron's charge, times by the potential, or the potential difference. So you always turn that into energies by doing EV. Electron volt is an energy. V is not an energy. It's related to the energy, but it's not an energy. Okay, so part BII asks for the frequency of the photon. So if we have that bit, then AII, we've got E equals to HF. That implies that F is equal to E over H. So we just put our values in. So we've got 1.66 times 10 to the power of minus 18 divided by Planck's constant, which is 6.63 times 10 to the minus 34. What does that give us? 2.51 times 10 to the 15 hertz. Part B is what frequency photon would make an electron jump to the first excited state. So the first excited state is going to be there. So we're going up. So the difference in energy there is what? 3.4. So we've got a difference of energy of 3.4 electron volts. So for part B, delta E equals to 3.4 EV. Let's turn that into joules. 3.4 times by 1.6 times 10 to the minus 19 joules. What does that give us? 5 point something? Just do 3.4 times 1.6 on the calculator. Do it on the calculator. 5.4 times 10 to the minus 19 joules. And then we're going to plug it into the same equation again. E equals to HF implies that F equals to E over H. So we do 5.4 times 10 to the minus 19 all over 6.63 times 10 to the minus 34. What does that give us?
$8.2
8.2 times 10 to the 14 hertz. Now we do a quick sanity check here. Sanity check. Basically, you use your common sense and you say, right, in the first question, we were at a higher energy level. Higher energy level has to correspond to a greater frequency. So let's just check. Is our frequency less than the first frequency we calculated? Because this frequency corresponds to the first energy level, which means it should be a lower frequency. And when we check, indeed, 10 to the 15 is greater than 10 to the 14. So that looks correct, right? If you got a number that was greater than your first number, then you know you've made a mistake. Okay, and then last bit was calculating the wavelength. Yeah? So for the wavelength, you can use the wave speed equation. C equals to F lambda. Or you could use the energy again and use E equals to hc over lambda. They're actually related to each other. So which one should we go for? Let's go for hc over lambda because we haven't been using that much. So E equals to hc over lambda. If we rearrange this, we get lambda equals to hc over E. Put our values in, 6.63 times 10 to the minus 34 times by the speed of light, which is 3 times 10 to the 8, all over the energy that we had from before, which was what, 5.4 times 10 to the minus 19. And what does this give us?
Um, 3.7 times 10 to the minus 7.
3.7 times 10 to the minus 7 meters. And that's the end of 2.2.3.